to discretize our unknown, let's take the voltage for example. We can write V in continuous space and time. If we discretize it, we'll say it's at position Z, but a discrete location with K is which discrete location, so it's an integer number of K values. And in time, I'm gonna use N for the nth time step. So integer, these are both integers. So Z and T ultimately do not have to be integers, but we're gonna be storing these at discrete integer number of locations. So I can write Zk is equal to K times delta Z. And K goes from 1 to some maximum integer, let's say K max. And then T, the nth value of T, the time is N times delta T. That's the nth time step. So N is the number of time steps. It goes from 1 to some maximum, let's say N max. So in other words, we are saying that we will solve for and store the values of the voltage at an integer number of Z locations in space and an integer number of locations in time that are separated by a distance delta T. Now, what would this look like if we were to draw out the grid in space? Let's say just in the Z direction along the transmission line. At the top of this slide is the first telegrapher's equation that we're considering right now. And on the bottom here, or in the middle, kind of, I'm showing a one-dimensional grid. So this is the Z direction. And it's going to start at, say, Z equals 0. And it's going to end at Z equal K max times delta Z. Because we have K, we're storing our unknowns at K max number of locations. And so in between, to keep things simple, we might imagine that there's going to be equally spaced discrete locations where we're going to be storing our unknowns. So this will be at delta Z, this will be at 2 times delta Z, and so forth. So here is our first voltage that we're storing. V is Z1, where K is equal to 1, Z2 here, and our last one is V Z K max, and here is the K max minus 1, goes down there actually. All right, so this is what the grid would look like. Right now we're just considering space. We're not considering how these are going to also be changing in time. So let's solve this first telegrapher's equation. We're going to solve this at each location of a voltage. We have to choose the location where we're going to solve this equation. So we're going to solve it at each of these discrete locations. And if we do this, we can see in the first term that we need to take the spatial derivative of the currents. And we want to use central differencing when we approximate this derivative here. So this means if we're going to use central differencing and we're going to say evaluate it, say right here at this voltage, that means we need to use a current value that's 1/2 of a cell to 1/2 here over to the left, and also 1/2 a cell to the right. So if we were to add a currents where we need to store the currents, we're going to have to store currents halfway between each of the voltages in order to be able to use central differencing. So now we can estimate the slope of the current at the position of the voltage. We're going to, here we're going to estimate the slope of the current at each of these locations of the voltage, because that's where we are solving this whole equation. So we'll write this out in more detail in a moment. First, let's consider the last term of this equation before we do that. So this is partial derivative with respect to time. This slide is the same as the last one, it's just that now we have the currents added in between the voltages. All right, so in the last term of the telegrapher's equation, this one right here, we see we need to take a partial derivative of the voltage with respect to time. We already decided to store the voltages at integer spatial locations. So, for example, here at z equals 0, z equals delta z. These are an integer number of delta z's these are being stored at. And we are also decided we're solving this equation at the locations of the voltage. So this equation is being solved at integer delta z locations. We would repeat solving this equation at every one of these integer delta z locations. So since the voltages are being stored at integer delta z's, let's say we're also going to store the voltages at integer time steps. So we would store it at t equals 0, and then t equals delta t, and then t equal 2 delta t, and so forth. So then here's a question for you. At what moment in time, we want to be able to say here, we're solving this at integer delta z locations, and at what moment in time do we want to also solve this equation? We have to pick a moment in time and in space at which we want to solve this equation. And when we solve this first telegrapher's equation, we want this equation to only call on values that we have stored in the computer. We don't want to call on a voltage that's at a half grid cell. That would be where we have currents stored. So we can't call on that location for a voltage. And since our voltages are stored at integer time steps in time, we just decided that here we're going to store the voltages at integer time steps in time. Then at what moment in time, what should we put here? Should we solve this first telegrapher's equation so that when we solve this equation, it only requires knowledge of the voltages at integer time steps as well as spatial positions, because those are stored in our computer. So what should we put here?